Hello, we are the Robotic End-Effector Automated Experimental Repetition Sewing Team, also known as the Reapers. Hi, I'm Trenton Whalen and I'm the team lead.
I'm Bradley Griffin and I'm the lead analyst for our team.
I'm Max Canellis, I'm the lead designer.
And I'm Charlie McClafferty, I'm the team cost analyst.
We're here at Southwest Research Institute, more specifically Division 10, Intelligent Systems. SWRI is a leader among independent, nonprofit research and development organizations. They specialize in everything from deep sea to deep space. At Division 10, they do all kinds of robotics work. Recently, they are interested in the field of automated sewing.
The field of textiles has come a long way since the first sewing machines were invented back in the 1800s. But things like baseballs and steering wheel covers are still hand sewn to this day. And that's because you can't run a normal, regular old sewing machine on these more complicated, solid surfaces.
That's why Southwest Research Institute has tasked us, the Reapers design team, with creating an end effector capable of sewing on three-dimensional curved surfaces with a solid core. An end effector is the hand of the robot that interacts with the environment and performs the desired reaction.
So this is pretty much the motion that they are looking for us to perform. Needle goes in this side, comes out over here, pulls through all the thread you're going to need, and then it moves back up and forth to the next position for the stitch. We'll need to do that a minimum of 3 times, and they aren't too concerned with speed, just function. Coming into this project, myself and the rest of the team didn't have any prior experience with sewing. My area of expertise lies in 3D modeling and programming, and unfortunately it's pretty difficult to run a computer simulation of thread moving through fabric.
You know, we could maintain control of the needle using a vise. As cost analysts, I help to quantify team progress and labor cost.
We could have the vise be pneumatically driven. Being the team lead for this project, I had previous leadership experience being a resident assistant, and I also had previous mechanical design experience working at Southwest Research Institute's Space Science and Engineering Division.
We could mount that all on an aluminum frame. As the lead analyst for our project, I was able to use a lot of the engineering knowledge that I've learned over the past few years in order to analyze our pneumatic system, determine the required needle holding force, and determine the strength of all of the bolts that were used for our project.
Some of the things Southwest expects from us for the project are that it must interface with the UR series robotic arm, it must be able to create a minimum of 3 consecutive linear stitches, and the total weight and force exertion by the end effector during sewing operation must be less than 22 pounds so as to not exceed the payload.
We settled on a pneumatically operated system, where a set of longer pistons move the needle back and forth, and a set of smaller pistons mounted onto the end grasp the needle in a little vise-type structure.
From some preliminary testing, it was determined that we need 0.5 pounds in order to insert the needle through our sewing material. In order to hold this needle steady during operations, it was determined that we need 0.4 pounds of force, and converting this to a pressure requirement for our pneumatic cylinder turned out to that we needed less than 1 psi supplied to our pneumatic cylinder. Since we have access to 60 psi, this was not an issue during our project.
Before we had our parts machined, we first had them 3D printed so that we could check all of the fits with our pneumatic pistons and to make sure there weren't any glaring oversights with the parts themselves.
Next, we had to have our custom fabricated parts machined. For this, we contacted the UTSA makerspace to machine our parts out of aluminum.
Now that we had the final design in hand, it was time to head to Southwest Research to begin testing and optimization of the actual programming of the robot.
To control our system, we have 4 2-position pneumatic solenoids, all sandwiched into one manifold. This gets its electrical signals from the robotic control box and its air source from the wall that can give us any pressure from 30 to 90 psi. The control box is connected to a laptop via an Ethernet cable, and the laptop is running a custom Python script that controls all movements of the robot arm and firing of all the pistons. This code is set up to allow the user to input how far apart they want the stitches and how many stitches total. From there, the code does some calculations and figures out how much thread it needs to pull through on each cycle.
So in order to prepare our test object for testing, we took our 1.25-inch diameter PVC pipe, cut it to length. We then wrapped it in a padding underlayer, secured that with tape. We then wrapped canvas around that padding, secured that with tape as well, and now our sewing object was ready to be tested. Once our sewing object was ready, we made a test mount out of wood. We had a wooden base and a wooden top. The top of the wood we split in half lengthwise with a hole cut out in the middle in order to hold our pipe. Once the mount and the sewing test object were assembled, we performed testing. We completed 16 tests and 6 compliance items. From this testing, it was determined that the maximum stitching capacity of the NED was 15 stitches, which met the 3-stitch requirement. The average stitching precision was about 3.28%. The overall weight of our End-Effector was about 4.2 pounds, and no needle errors, thread errors, or fabric errors were recorded during these trials.
With completion of the NED, the team has spent $1,962 out of the $3,000 originally allocated for our project. This will put us well under budget. This project has turned out to be a true labor of love, with over 1,372 man-hours expended by the team. This has led to a labor cost estimate of $82,000 based on representative, fully loaded industry rates.
Southwest Research Institute was very pleased with the product that we produced. Not only did it give our team a lot of mechanical design experience, building, testing, and verifying a design, but it also laid the groundwork for future automated sewing development.